All right, so you've got that AP Chem exam tomorrow, huh? Getting ready to dive into ethers and imines.
Yeah, organic chemistry can definitely feel like a whole other language sometimes, but don't worry, we're going to break it down for you.
And make sure you're totally prepped to ace that test.
Exactly. What's really cool about ethers and imines is that they're not just like abstract chemistry stuff.
Right.
They're actually all around us in medicines, fuels, even like the smells of flowers.
Oh, that's a good point. Okay, so let's start with ethers. I remember learning about how they used to use them as anesthetics.
Oh yeah, diethyl ether was a total game changer for surgery. Back then, anesthetics were pretty basic, so using ether, which evaporates super quick into a vapor,
Right.
was huge. Patients could just inhale it for controlled anesthesia. Of course, we have safer options now, but still.
Yeah, totally. It's crazy how something that seems simple, like something evaporating quickly, can have such a big impact.
Absolutely.
But before we get too ahead of ourselves, let's back up a bit. What exactly is an ether?
At its core, an ether molecule has an oxygen atom bonded to two carbon atoms.
Okay.
That's what we call the ether functional group. Now, those carbon atoms, they can be part of the same group of atoms, making a symmetrical ether,
Okay.
or they can be different, creating an asymmetrical ether.
So it's like the oxygen is the main character, and the carbon groups are its sidekicks.
Exactly.
Determining the ether's, personality.
Precisely. Take diethyl ether, for example. It's got two ethyl groups, which makes it symmetrical, and it's known for being super volatile, remember, which made it a good anesthetic back in the day, and it's also used as a solvent.
Gotcha. So the type of carbon group attached to that oxygen really shapes what the ether does.
For sure. And speaking of different roles, let's talk about how we name these ethers. It can seem intimidating, but it's actually a pretty logical system.
All right, I'm ready to decode the language of ethers. What's the first step?
Okay, so first, you gotta identify the two groups attached to the oxygen.
All right.
Let's take CHOCH as an example. Here we've got a methyl group and an ethyl group. To get the common name, arrange them alphabetically and add ether at the end.
So in this case, it would be ethyl methyl ether.
You got it? Pretty straightforward, right?
Yeah, totally. But my teacher also mentioned something called IUPAC nomenclature.
Ah, yes.
Does that change things up?
A bit. In the IUPAC system, you take the smaller group, in our example, that's methyl, and change it to methoxy.
Okay.
Then you look at a longest carbon chain, which is ethane, and you combine them to get methoxyethane.
So it's like methyl ether and methoxyethane are just two different nicknames for the same molecule.
Exactly. Think of it like that. And trust me, getting comfortable with these naming conventions will be super helpful for your exam.
So we've got the structure and naming down. What about the properties of ethers? What makes them unique?
One key difference between ethers and their close cousins, the alcohols, is that ethers have lower boiling points.
Interesting. Why is that?
Well, alcohols have these strong hydrogen bonds. Think of them like a super strong glue holding the molecules together.
Okay.
Ethers don't have those strong bonds, so they evaporate more easily.
So in a boiling point battle, alcohols would win because of their hydrogen bond glue.
You got it. Now, ethers can dissolve in water to a certain extent thanks to that oxygen atom.
Right.
But as those carbon groups hanging out with the oxygen get bigger, the ether is less and less likely to mix with water.
So it's like the carbon groups are telling the oxygen, hey, let's steer clear of the water.
Haha, exactly. And in terms of reactivity, ethers are generally pretty chill.
Okay.
But they do have a weakness. Strong acids can break that ether bond, splitting the molecule in two.
Like kryptonite for ethers.
Pretty much. But even though they're not super reactive, ethers are still really useful.
Right. We already talked about their history as anesthetics. What about today?
Well, today they're commonly used as solvents in labs and industries.
Oh, okay.
They play a big role in making sure chemical reactions run smoothly.
Like the unsung heroes of chemistry, making sure everything works.
You could say that. They're also added to fuels to make them burn more efficiently.
So they're like fuel performance enhancers.
Exactly. Think of it as giving the fuel an extra boost to burn cleaner.
This is making a lot more sense now. What about in pharmaceuticals? Do ethers play a role there?
Yeah, definitely. While they might not always be the stars of the show, ethers are essential behind-the-scenes players in pharmaceuticals.
Okay.
They act as intermediates in drug synthesis, meaning they're part of the building blocks for creating important medications.
Wow, so ethers are important for making medicines and helping deliver them in the body. That's amazing. Okay, we've learned a lot about ethers, from their structure and naming to their properties and uses, but we've got another key player to talk about: amines.
Right. And just like with ethers, understanding amines starts with their structure.
Okay, let's hear it.
Amines are like descendants of ammonia, which you might know for its pretty strong smell.
Oh yeah, definitely. So ammonia is like the parent molecule, and amines are its kids.
Exactly, inheriting some of those fragrant characteristics.
Okay, so remind me, what's the formula for ammonia?
Ammonia is NH off. Now, amines form when one or more of those hydrogen atoms in ammonia get replaced by what we call alkyl or aryl groups.
It's like a swap meet, trading out hydrogen for alkyl or aryl groups. But does it matter how many hydrogens get replaced?
Good question. It does. We group amines as primary, secondary, or tertiary.
Oh, okay.
Based on how many hydrogens are replaced. A primary amine has one hydrogen replaced, a secondary amine has two swapped out, and a tertiary amine has all three hydrogens traded.
Okay, so I'm picturing this. A primary amine has one alkyl or aryl group attached to the nitrogen, a secondary has two, and a tertiary has three.
Exactly, you're getting it. And just like we saw with ethers, the type and number of those alkyl or aryl groups really shape the amine's properties and how it interacts with other molecules.
So it's all about those sidekicks again, shaping the main character's behavior. Do you have any examples of these different types of amines?
Sure. A classic primary amine is methylamine, CHNH, which is used in making pesticides.
Okay.
Then for secondary amines, we've got dimethylamine, CHNH-CH, often used in the rubber industry.
Interesting.
And for tertiary amines, there's trimethylamine, which contributes to that fishy smell we associate with, well, fish.
Wow, I never realized amines were hiding in so many everyday things.
They're everywhere.
Okay, so we've tackled the structure and classification of amines. What's next?
Next up is naming those amines, and thankfully, it's another logical system, just like with ethers.
All right, I'm ready for more chemical decoding.
All right. The IUPAC rules are all about finding the longest carbon chain that's attached to the nitrogen atom.
Okay.
Let's say our longest chain is protane.
All right.
We replace the E at the end with amine, giving us propanamine.
Propanamine, got it.
Now, if there are any other groups attached, we add them as prefixes, and if they're directly attached to the nitrogen, we use N to show that.
So it's like we're identifying the main chain and then giving a shout out to any side groups with a special N badge for those bonded directly to the nitrogen.
Exactly. For example, dimethylamine has two methyl groups attached to nitrogen, right? But you could also have ethylmethylamine, where an ethyl and a methyl group are both attached.
So M tells us those groups are hanging out right on the nitrogen. Got it. Now, what about those tertiary amines with three alkyl groups? How do we name those?
Same rules apply. Trimethylamine would have three methyl groups on the nitrogen, and you can get even more complex, like ethylbumethylamine with an ethyl and two methyl groups.
Wow, this amine language is starting to make sense. So we've got structure, classification, and naming down. What about their properties? Do amines have any quirks that set them apart?
Definitely. One key property is that primary and secondary amines can form those hydrogen bonds we talked about.
Oh, right, because they still have those hydrogens attached to the nitrogen.
Exactly. This gives them higher boiling points compared to those tertiary amines, which don't have the hydrogens for hydrogen bonding.
Those hydrogen bonds always influencing how molecules behave. Anything else about their properties that we should know?
Well, many amines, especially the smaller ones, have that distinct odor we talked about earlier.
The fishy or ammonia-like smell.
Yep, that's usually a good sign you're dealing with a amine.
So if something smells a bit fishy, chances are there's an amine involved. Speaking of being involved, where do we actually find these compounds in the real world?
Amines are surprisingly versatile. You'll find them in a ton of pharmaceuticals, from antihistamines to anesthetics to antidepressants.
Wow, that's a wide range. How do they work in such different medications?
What's fascinating is how they interact with all sorts of biological molecules.
Okay.
Thanks to those nitrogen-containing functional groups, this makes them super valuable for targeting specific receptors in the body.
So they're like little molecular messengers, delivering specific instructions to our cells.
You got it. Amines are also important in making dyes.
Really?
Yeah. Aniline, a type of amine, is a key ingredient in a lot of dyes.
So the colorful clothes we wear might have amines to thanks for their vibrancy. That's cool. Are there any other applications for amines?
Tons. They're also widely used in agriculture.
Okay.
As the building blocks for things like pesticides, herbicides, and fungicides.
Wow, so they're not only adding color to our world, but they're also helping to ensure we have enough food to eat. Do you have any specific examples of how amines are used in these areas?
Of course. Remember methylamine, the primary amine we discussed earlier.
Yeah.
It's commonly used in pesticides. And then you have aniline, the workhorse of the dye industry. And in pharmaceuticals, dimethyltryptamine, or DMT, which is an amine found in some plants, is being studied for its potential therapeutic benefits.
Okay, this is all really starting to come together. We've covered the structure, classification, naming, properties, and even applications of amines. Now I think it's time to shift gears a bit and dive into another important group of organic compounds, alkanes and alkenes.
Sounds good. Alkanes are the simplest hydrocarbons, meaning they're only made of carbon and hydrogen atoms.
Right, the basics.
And the key thing to remember about them is they only have single bonds between their carbon atoms. This makes them what we call saturated hydrocarbons.
So they're like the single and ready to mingle hydrocarbons.
Aha, you could say that. Because they're saturated, they have the maximum number of hydrogen atoms possible for their structure, which follows the general formula CHH, where N is the number of carbon atoms.
Right, that formula helps us figure out how many hydrogens are in an alkane based on how many carbons it has. Can you give me some examples of alkanes to see how this works in practice?
Absolutely. The simplest alkane is methane, CH, with 1 carbon and 4 hydrogens. Then we have ethane, CH, with 2 carbons and 6 hydrogens. And as we add more carbons, we get propane, CHA, butane, CHS, and so on.
Okay, I see the pattern. So as the number of carbons increases, the number of hydrogens increases too. But what about their properties? What makes alkanes stand out?
Well, because they only have those single bonds, alkanes are pretty unreactive. Those single bonds are strong and stable, so they're not really looking to change. They're kind of like the content and settled down members of the organic compound family.
So they're not looking for any drama in their molecular life.
Exactly. But even though they're not very reactive, they're still incredibly useful. Think about the fuels we use every day: natural gas, which is mostly methane, or propane, which is used for grilling. Those are all alkanes.
Wow, so they're the powerhouses behind our cooking and heating.
Right. When alkanes burn, they release a lot of energy.
Okay, we've got alkanes covered. Now, what about alkenes? How do they differ from their single-bonded cousins?
Alkenes are still hydrocarbons, but they're a bit more adventurous. Instead of just single bonds, they have at least 1 double bond between carbon atoms. This double bond makes them unsaturated hydrocarbons, meaning they're a bit more open to reacting with other substances.
So alkenes are like the looking for a good time hydrocarbons.
Haha, that's a good way to put it. And because of that double bond, they have fewer hydrogen atoms compared to alkanes, following the general formula CH.
Okay, I'm ready for some examples of alkenes. What are some common ones?
A classic example is ethene, CH, which has 2 carbons joined by that double bond. Then you have propene, CH, with 3 carbons. Notice how the number of hydrogens is always double the number of carbons.
Yep, I see the pattern. So because of that double bond, alkenes must be more reactive than alkanes, right?
You got it. That double bond is like a beacon signaling to other molecules that they're open to forming new connections. They readily undergo what we call addition reactions, where the double bond breaks open and new atoms or groups of atoms are added to the carbon chain.
So they're the social butterflies of the organic compound world, always ready to make new friends. Do you have any examples of these addition reactions?
Absolutely. A classic test for alkenes is reacting them with bromine water, which has a reddish-brown color. When bromine water is added to an alkene, that double bond breaks open and the bromine atoms attach to the carbons. This causes the solution to lose its color, becoming colorless. It's pretty cool to see.
Wow, that really brings it to life. So the double bond makes alkenes more reactive than alkenes. But even though they're more reactive, they must still have important uses, right?
Of course. Think about plastics. Ethene, for example, is used to make polyethylene, which is what plastic bags and milk jugs are made of. And propene is used to make polypropylene, which is often used for things like food containers.
So even though they're more reactive, alkenes are still incredibly important. Okay, we've covered alkanes and alkenes. Now, what about those aromatic hydrocarbons? Those always sounded kind of fancy.
They are interesting. Aromatic hydrocarbons are all about a special ring structure called the benzene ring. This benzene ring is a 6-membered ring of carbon atoms with alternating single and double bonds. But here's the catch. Those electrons in the double bonds aren't actually confined to those specific bonds. They're shared across all 6 carbon atoms in what we call delocalization.
Okay, I'm trying to picture this delocalization thing. What does that mean for the benzene ring?
Basically, it means that the benzene ring is super stable. It doesn't react as easily as you might think, considering it has those double bonds. It's like those electrons have created this super strong bond of friendship, and the whole ring is very resistant to breaking apart.
So it's like the benzene ring has extra protection thanks to those delocalized electrons.
You got it. And this stability is one of the key reasons why aromatic hydrocarbons are so unique and important.
Okay, I'm ready for some examples of these aromatic hydrocarbons. What are some common ones?
The most basic one is benzene itself, CaH. Then you have toluene, CHH, which is just benzene with a methyl group attached. And naphthalene, CH, the stuff in mothballs, is made of 2 benzene rings fused together.
So they all have that benzene ring at their core. But what about naming these aromatic hydrocarbons? Is there a special system for that, like we saw with ethers and amines?
There is. Simple ones like toluene have common names, but for those with more complex structures and multiple groups attached, we use IUPAC rules.
Okay, I'm ready for a quick crash course in naming aromatic hydrocarbons using IUPAC rules.
All right, let's use toluene as our example. Its IUPAC name is methylbenzene, which tells us it's a benzene ring with a methyl group attached. Now imagine we have something called 1,3-dinitrobenzene. What would that look like?
Okay, that sounds a lot more complicated. How do we break that down?
Dinitro means we have two nitro groups, attached to the benzene ring,
Okay.
and 1,3 tells us where they're located on the ring.
So we've got a benzene ring with nitro groups at positions 1 and 3. Got it. But what about those aromatic hydrocarbons themselves? Are they just interesting structures, or do they actually have any real-world applications?
They definitely have real-world uses. Toluene is a common solvent, and it's also used to make TNT.
Oh, wow.
And remember naphthalene? It gives mothballs their distinctive smell. Many aromatic hydrocarbons are also found in essential oils, which are used in perfumes and flavorings.
That's so interesting. So aromatic hydrocarbons are more common than I realize. Okay, we've explored alkanines, alkenes, and even aromatic hydrocarbons. Now I think we need to talk about another important class of organic compounds, organic acids, alcohols, and esters.
Great idea. These are all examples of what we call functional groups.
Right, we touched on those earlier.
These functional groups are like specific sets of atoms that give organic molecules their characteristic properties.
Okay.
It's like adding a special accessory to a basic outfit. It completely changes the look and feel.
I like that analogy. So functional groups are like the fashion designers of the organic compound world, adding a bit of flair to those hydrocarbon chains. Can you remind me of some examples of these functional groups?
Sure. Some of the most common ones you'll see in AP chemistry are organic acids, alcohols, esters, ethers, aldehydes, ketones, and amines.
Okay, we've already talked about alcohols, esters, ethers, and amines in detail, so what about those other three? Organic acids, aldehydes, and ketones.
Let's start with organic acids, which are also called carboxylic acids. They have a carboxyl group, which is written as -mo, attached to a carbon chain.
Okay.
This carboxyl group acts like a tiny chemical factory, able to donate a hydrogen ion, or Hu, to a solution.
So that's what makes them acidic. What are some examples of organic acids that we might see every day?
Well, you probably have one in your kitchen right now.
Really?
Acetic acid is the main component of vinegar. Then there's formic acid, which gives ants their sting, and citric acid, which adds that tartness to citrus fruits.
Wow, organic acids are adding a lot of zing to our lives, both literally and figuratively. Now, what about aldehydes and ketones? How are they different from each other?
Aldehydes and ketones both contain what's called a carbonyl group, written as CEO. It's a carbon atom double bonded to an oxygen atom.
Gotcha.
The key difference is where that carbonyl group is located. In an aldehyde, it's always at the end of a carbon chain,
Okay.
while in a ketone, it's somewhere within the chain.
So it's all about location, location, location. Are there any easy ways to remember which is which?
Absolutely. Think about it this way. Aldehydes have that al at the end of their name, just like their carbonyl group is at the end of the chain. And ketones usually have that one sound in their name, reminding you that the carbonyl group is somewhere in the middle of the chain.
I like those memory tricks. So aldehydes have their carbonyl group at the end, ketones have it in the middle. But does this difference in location actually affect how they behave?
It totally does. Aldehydes are easily oxidized,
Okay.
meaning they react readily with oxygen to form carboxylic acids.
Oh, interesting.
That's why many aldehydes have a sort of sour or pungent odor, because they can slowly oxidize in the air.
So they're slowly turning into those tanky organic acids right under our noses.
You got it.
What about ketones? Are they easily oxidized too?
Ketones are a bit more resistant to oxidation, making them more stable and less likely to have those strong odors.
Interesting. So aldehydes are more reactive and can be a bit smelly because they're easily oxidized, while ketones are more stable and generally less odorous. But where do we actually encounter aldehydes and ketones in the real world?
You'll find them in all sorts of natural and synthetic products. Many fragrances and flavorings contain aldehydes and ketones because they often have these pleasant fruity or floral scents.
Okay.
For instance, beta-aldehyde gives almonds their characteristic almond-like aroma, and vanillin is what makes vanilla smell so sweet and creamy.
Wow. So those delicious smells are thanks to aldehydes and ketones. What other interesting applications do they have?
Formaldehyde, the simplest aldehyde, is used as a preservative and disinfectant, and acetone, a simple ketone, is a common solvent found in nail polish remover and paint thinner.
So they're not just about pleasant smells, they have some practical uses too. Okay, we've covered a lot of ground with functional groups, but there's one more important topic we need to discuss: organic reactions.
Great point. Understanding organic reactions is all about recognizing how those functional groups change and interact with other molecules. One key reaction you'll want to know is esterification.
All right, give me the rundown on esterification. Why is it so important?
Well, esterification is how esters are made. Remember those fragrant esters that give fruits and flowers their delightful smells?
Yeah.
That's esterification in action.
So it's like a chemical love story between alcohols and carboxylic acids, resulting in the birth of a fragrant ester.
I like that.
So what exactly is going on in this reaction?
The main players are, of course, the alcohol and the carboxylic acid. You also need a catalyst, usually a strong acid like sulfuric acid, to help speed things up. And typically, you need to heat the mixture to get the reaction going.
So we're setting the mood for a chemical romance with some heat, and we got a strong acid chaperone, making sure the alcohol and carboxylic acid can get together. What happens next?
The result is an ester, along with water as a byproduct. It's like a chemical equation for a happy relationship. Alcohol plus carboxylic acid makes an ester and water.
I love how you're making this so relatable. So esterification is how we get those amazing smells in fruits and flowers. But are there any other uses for this reaction?
Oh yeah, esterification is used in tons of different industries, like making polyesters, which are found in fabrics, plastics, and films. It's even used to make biodiesel, a renewable fuel made from vegetable oils or animal fats.
So esterification isn't just about pretty smells. It's also involved in creating essential materials and even alternative fuels amazing. Okay, so we've talked about esterification. Are there any other important organic reactions we should know about?
Another one to understand is saponification. This reaction is the key to making soap.
Soap making? That sounds intriguing. What exactly is saponification and how does it lead to soap?
Saponification is basically the reverse of esterification. Instead of forming an ester, we're breaking it apart.
Okay.
It's this process that forms the basis of soap making.
So it's like a chemical uncoupling, breaking that ester back down into its original alcohol and carboxylic acid. How does that make soap?
Well, in soap making, the esters that get broken down are called triglycerides. Those are just fats and oils. When these triglycerides react with a strong base, like sodium hydroxide or potassium hydroxide, in water, they go through something called hydrolysis.
Hydrolysis, that sounds like water's involved.
You're right. Hydrolysis basically means breaking down a molecule using water. In saponification, water helps break those ester bonds in the triglycerides.
Okay, so we have triglycerides, a strong base, and water all mixed together. What happens then?
The triglycerides get broken down into glycerol, which is a type of alcohol, and the sodium or potassium salts of fatty acids. And guess what? Those salts of fatty acids are what we call soap.
So soap is basically a byproduct of breaking down triglycerides with a strong base. That's pretty cool. But how does soap actually work? What makes it so good at cleaning things?
Soap molecules have this really cool structure that lets them interact with both water and oil.
Okay.
One end of the soap molecule is hydrophilic, meaning it loves water.
Right.
But the other end is hydrophobic, meaning it hates water and loves oil.
So soap is kind of like a double agent, playing for both teams.
Exactly. It can hang out with water and oil. This dual nature is what makes soap such a good cleaner. When you mix soap with water, those soap molecules form these tiny structures called micelles.
Micelles, what are those?
In a micelle, all the hydrophilic ends of the soap molecules point outward toward the water,
Okay.
and all the hydrophobic ends cluster together in the center.
So it's like the soap molecules form these little bubbles with an oily core and a watery exterior.
You got it. Now, when you apply soap to something dirty, those hydrophobic ends attach to the grease and oil.
Okay.
While the hydrophilic ends stay dissolved in the water, this lets the soap lift the dirt and oil away from the surface and into the water, where it can be rinsed away.
It's like the soap creates tiny life rafts that carry away the dirt and oil.
That's a great way to think about it, and that's the basic science of how soap cleans, all thanks to the reaction of saponification.
This has been an amazing journey through organic chemistry. We've covered so much: hydrocarbons, functional groups, reactions, and even how soap works. I feel like I've learned so much. Is there anything else we need to touch on before that big exam?
Well, there's one more thing related to ethers that we should go over just to be extra sure you're ready for anything. It's the difference between symmetrical and asymmetrical ethers.
Okay, I remember you mentioning that earlier, but can you refresh my memory on what makes an ether symmetrical or asymmetrical?
For sure. It all boils down to the two groups attached to that central oxygen atom in the ether molecule. If those two groups are the same, like two methyl groups or two ethyl groups, we call it a symmetrical ether. Think of it like a perfectly balanced scale with the same weight on both sides.
Okay, so symmetrical ethers have matching buddies for their oxygen atom. Got it. What about asymmetrical ethers? What makes them different?
Asymmetrical ethers are those where the two groups attached to the oxygen are different. It's like having a scale with different weights on each side that throws off the balance. For example, if you have a methyl group on one side and an ethyl group on the other, you've got an asymmetrical ether.
Ah, I get it. It's all about comparing the oxygen sidekicks. If they're the same, it's symmetrical. If they're different, it's asymmetrical. But does this actually matter? Does it affect how the ether behaves in any way?
Yeah, it can actually influence the ether's properties. For instance, symmetrical ethers often have slightly higher boiling points compared to asymmetrical ethers that have the same number of carbon atoms.
Really? So symmetrical ethers are a little more stubborn about boiling. Why is that?
It all comes down to how those molecules are shaped and how they pack together. Symmetrical ethers tend to be a bit more compact and can fit together more snugly. This leads to stronger attractions between the molecules, which results in a slightly higher boiling point.
So even a small change in those groups attached to the oxygen can affect the ether's physical properties. That's pretty neat. Are there any other situations where being symmetrical versus asymmetrical makes a difference?
You're asking all the right questions. In some chemical reactions, particularly those where you're breaking that ether bond, symmetrical ethers might react a bit differently than asymmetrical ethers. But for the most part, the main distinctions are in those physical properties we talked about, like boiling point and sometimes melting point.
Okay, so it's a good idea to keep this symmetrical versus asymmetrical difference in mind, especially when you're comparing different ethers. I feel much more confident about those ether questions on the exam now.
I'm glad to hear that. Remember, organic chemistry is all about understanding those patterns and connections. Once you've got the basics down, you can apply that knowledge to all sorts of molecules and reactions.
And that's what the deep dive is all about, helping you see the big picture and how everything fits together. Okay, we've covered a lot of ground today.
Yeah, we have.
Are there any last words of wisdom or advice you'd like to share before our listener takes on that AP chemistry exam?
Absolutely. Remember, organic chemistry is all about logic and patterns. Focus on those fundamental concepts, like the structure and bonding of organic molecules, the different functional groups and what makes them unique, the major types of organic reactions, and those all-important naming conventions. Practice naming compounds, visualize those reactions, and don't be afraid to draw out those structures to help solidify your understanding. You've got this.
That's great advice. And remember, even though organic chemistry might seem a little intimidating at first, it's a really fascinating and rewarding subject. Once you start to see how these molecules connect to the world around us, it can really spark a lifelong curiosity about the amazing complexity of chemistry.
Well said. And on that note, I think we'll wrap up this deep dive into the world of organic chemistry. We hope you found it helpful, and best of luck on your exam.
Thanks for joining us on the deep dive. We'll catch you next time for another exciting journey of discovery.
See you then. You're right. It really is. It's all about looking at those groups on either side of the oxygen. If they're the same, it's symmetrical. If they're different, it's asymmetrical. But now you might be thinking, does that even matter?
Yeah, that's a good question. Does it change how the ether acts, whether it's symmetrical or asymmetrical?
It can, actually. Like, symmetrical ethers tend to have slightly higher boiling points than asymmetrical ethers if they have the same number of carbon atoms, that is.
Wait, why would symmetrical ethers boil at higher temperatures?
It's all about their shape. Really, symmetrical ethers, they're usually more compact, so they can pack in closer together.
Okay.
And that means stronger attractions between the molecules, which leads to a slightly higher boiling point.
So just a little tweak to those side groups can change how an ether behaves physically. Pretty cool. Are there any other times where that symmetrical or asymmetrical thing matters?
You're good at picking up on those details. In some reactions, yeah, especially if you're breaking that ether bond, symmetrical ethers might react a bit differently compared to asymmetrical ethers, but mostly the main difference is in those physical properties, like we talked about, boiling point, sometimes melting point.
Okay, so it's good to remember that symmetrical versus asymmetrical thing, especially when comparing different ethers. I feel much better about ethers now, thanks to you.
Glad to hear it. And remember, organic chemistry is all about recognizing patterns and connections, Once you've got those basic ideas down, you can apply them to all kinds of molecules and reactions.
That's what the deep dive is all about, helping you see the big picture. All right, let's move on. What about alkanes?
Okay, alkanes, so these are the simplest kind of hydrocarbon, just carbon and hydrogen atoms connected by single bonds.
Like the starting point for organic chemistry, right?
Exactly, and because they only have those single bonds, we call them saturated hydrocarbons, meaning they've got the maximum number of hydrogen atoms possible.
So they're like completely full, no room for anything else.
That's a good way to put it. Now, remember that general formula, CHH?
Yeah, vaguely.
That applies to alkanes. N is the number of carbon atoms.
Right. It helps you predict how many hydrogens an alkane will have.
You got it. So, for example, the simplest alkane is methane, CH, 1 carbon, 4 hydrogens. Then we have ethane, CH, 2 carbons, 6 hydrogens.
Okay.
Then as we add more carbons, we get propane, CH, butane, CH, and so on.
Okay, so the pattern is pretty clear. As the number of carbons goes up, so does the number of hydrogens. But what about their properties? What makes alkanes special?
Well, because of those single bonds, alkanes are, generally speaking, pretty unreactive. Those single bonds are strong, they're stable, not really looking to change, sort of like the introverts of the molecule world, happy, just chilling on their own.
No drama in their lives.
Not really, but don't underestimate them. Even though they're not very reactive, they're still super useful. Think about the fuels we use all the time, natural gas, that's mainly methane propane, for grilling gasoline. all mostly made up of alkanes.
Wow, so they're the power behind our cooking and heating. Who knew?
Exactly. When those alkenes burn, they release a ton of energy.
Makes sense. Okay, so we've got the lowdown on alkanes. What about their more lively relatives, the alkenes? What sets them apart?
Alkenes, they're still hydrocarbons, but they're a bit more, shall we say, outgoing, ready to react. Instead of just single bonds between carbons, they've got at least one double bond. That double bond makes them unsaturated, meaning they're more open to reacting, making new connections.
So alkenes are the social butterflies of the hydrocarbon world.
Haha, exactly. And that double bond means they have fewer hydrogens compared to alkanes. The general formula for them is CH.
Okay, fewer hydrogens. Can you give me some examples of alkenes?
Of course. A classic one is ethene CH, 2 carbons connected by that double bond. Then there's propene CH with 3 carbons. See how the number of hydrogens is always double the number of carbons.
Yeah, I see it. So those alkenes, with their double bonds, they must be more reactive than alkanes, right?
You're catching on quick. That double bond is like a signal to other molecules saying, hey, I'm open to making new bonds. They're really good at undergoing addition reactions where the double bond breaks and new atoms, or even groups of atoms, get added to those carbons.
So they're welcoming new members into their little carbon club. Do you have any examples of those addition reactions? Just to help me picture it.
Sure. A classic test for alkenes is using bromine water. Bromine water has this like reddish-brown color. But when you add it to an alkene, the double bond breaks and those bromine atoms attach to the carbons. The solution loses its color, turns colorless. It's a neat little trick.
That's a really clear way to see how that double bond makes the alkenes so reactive. But even though they're more reactive, I'm guessing alkenes still have some important uses, right?
Absolutely. Think about plastics, for example. Lots of plastics are made from alkenes. Like ethene is used to make polyethylene, which is in everything from plastic bags to milk jugs. And propene is used to make polypropylene, which is often used for food containers.
So even though they like to react, alkenes are still super important.
That's right. They're all around us.
Okay, alkenes, check. What's next on our hydrocarbon adventure?
Let's talk about a special group called aromatic hydrocarbons. They get their name because they often smell kind of nice, but what really makes them special is a ring structure called the benzene ring.
Okay, benzene rings, I feel like I've heard of those. What's so unique about them?
So a benzene ring, it's a 6-membered ring of carbon atoms.
6 carbons, okay.
With alternating single and double bonds. But here's the twist. Those electrons in the double bonds, they're not just stuck in one place. They're actually shared across all 6 carbon atoms in what we call delocalization.
Delocalization, that sounds complicated. Can you break that down for me?
Imagine those electrons are like a team passing a ball back and forth. They're constantly moving around the whole ring, not stuck in one position.
Okay, so the electrons are always on the move, shared by all the carbon atoms in the ring. What does that do to the benzene ring itself?
That delocalization makes the benzene ring incredibly stable, much less reactive than you might think for a molecule with double bonds. It's like those electrons have formed this super tight bond, and the whole ring is super tough to break apart.
So it's got like a built-in shield protecting it from being disrupted.
Exactly. And this stability is one of the big reasons why aromatic hydrocarbons are so fascinating and important.
All right, so what are some common aromatic hydrocarbons we might come across?
The most basic one is just benzene itself, CH. Then you have toluene, CHH, which is benzene with a methyl group attached.
Okay.
And naphthalene, CH-at, which you find in mothballs, is made of 2 benzene rings stuck together.
So it's all about that benzene ring being the core. But how do we name these things? Is there a system, like with ethers and amines?
You bet. For the simple ones, like toluene, they usually just go by their common names. But when things get more complex with multiple groups attached, we turn to the IUPAC rules.
All right, hit me with a quick IUPAC naming lesson for aromatic hydrocarbons.
Okay, let's use toluene again. Its IUPAC name is methylbenzene. Pretty straightforward, right? Tells you it's benzene with a methyl group attached.
Yeah, that makes sense.
Now, what if we have something called 1,3-dinitrobenzene?
That sounds a lot more complicated. How do we decipher that?
Okay, dinitro means there are 2 nitro groups, on the benzene ring.
Got it.
And 1-CoA3 tells you where they're located. So you've got a benzene ring with nitro groups at positions 1 and 3.
Like they have assigned seats on the benzene ring? Okay, I see the logic. But are these aromatic hydrocarbons just interesting structures, or do they actually have any real-world applications?
They have a ton of uses. Toluene is a common solvent, and it's used in making TNT, believe it or not.
No way.
Yeah, and naphthalene, that's what gives mothballs their distinctive smell. Lots of aromatic hydrocarbons are also found in essential oils, which are used in perfumes and flavorings.
Wow, so aromatic hydrocarbons are much more common than I thought. Okay, we've covered alkanes, alkenes, even aromatic hydrocarbons. Now let's switch gears and talk about another big category, Organic acids, alcohols, and esters.
Good idea. These are all examples of what we call functional groups.
Right, we touched on those earlier. They're like add-ons that give the molecules special properties.
You got it. There's specific groups of atoms that give those organic molecules their unique characteristics. It's like adding a cool accessory to a plain outfit. Changes the whole look and feel.
I like that analogy. So they're like the fashion stylists of the organic compound world, giving those hydrocarbons some personality. Can you remind me of some examples of functional groups?
Absolutely. Some common ones you'll come across in AP chemistry are organic acids, alcohols, esters, ethers, aldehydes, ketones, and amines.
Okay, we already went over alcohols, esters, ethers, and amines, so what about the others? Organic acids, aldehydes, and ketones.
Let's start with organic acids, also known as carboxylic acids. Their defining feature is a carboxyl group, minus keo, attached to a carbon chain.
Okay, so that carboxyl group is what makes them acidic.
Exactly. That carboxyl group can donate a hydrogen ion, H-boo, which is what makes a solution acidic. You've probably tasted plenty of organic acids without even realizing it.
Like what?
Well, acetic acid is the main ingredient in vinegar, so there's that formic acid is what gives antbites their sting, and citric acid is what makes citrus fruits taste so tart.
Wow, so organic acids are adding a lot of flavor to our lives.
You could say that.
What about aldehydes and ketones? How are they different from each other?
Both aldehyde and ketones have what we call a carbonyl group, written as C-E-G-O. It's a carbon atom double bonded to an oxygen.
All right.
But the key difference is where that carbonyl group is. In an aldehyde, it's always at the end of the carbon chain. In a ketone, it's somewhere within the chain.
So it's all about location, location, location. Any easy tricks for remembering which is which?
Definitely. Think of it this way. Aldehydes have that al at the end of their name, just like their carbonyl group is at the end of the chain. And ketones often have that one sound in their name, which can remind you that the carbonyl group is somewhere in the middle.
Ooh, I like those. Aldehyde, end of the chain ketone, somewhere in the middle. But does that difference in location actually matter? Does it change how they act?
It definitely can. Aldehydes are very easily oxidized, meaning they react really easily with oxygen, forming those carboxylic acids we talked about.
Right.
That's why a lot of aldehydes have a slightly sour or sharp smell, because they're slowly oxidizing in the air.
So they're like turning into those tangy organic acids right under our noses.
Exactly.
What about ketones? Do they oxidize easily too?
Not as much. Ketones are more resistant to oxidation, so they're more stable and usually don't have those strong smells.
Okay, so aldehydes are more reactive and can be a bit smelly because they oxidize easily, while ketones are more stable and generally less odorous. But where do we actually find aldehydes and ketones in real life?
You'll find them all over the place. Lots of fragrances and flavorings have aldehydes and ketones in them because they often have pleasant, fruity, or floral scents.
Makes sense.
For example, benzaldehyde is what gives almonds their almond-like aroma, and vanillin is what makes vanilla smell so delicious.
Wow, so those delicious smells are thanks to aldehydes and ketones. What other cool uses do they have?
Well, formaldehyde, which is the simplest aldehyde, is used as a preservative and a disinfectant.
Okay.
And acetone, a simple ketone, is a common solvent that you find in things like nail polish remover and paint thinner.
So they're not just about smelling nice, they have some practical uses too. All right, we've talked about organic acids, alcohols, aldehydes, and ketones. So we've covered a lot about functional groups, but there's one more important topic: organic reactions. We mentioned esterification before, but can you remind me why that reaction is so important?
Of course. Esterification is how we make esters, remember?
Right, from an alcohol and a carboxylic acid?
Exactly. And it's the reaction behind so many of those natural and artificial flavors and fragrances we encounter every day.
Yeah, it's not just about the structures of the esters themselves, but also how they're made through this key chemical reaction. You mentioned that a catalyst is needed to help this reaction along.
You're right. Usually it's a strong acid like sulfuric acid that acts as a catalyst, helps the alcohol and carboxylic acid react more efficiently, and often we need to heat things up a bit to get the reaction going.
It's like we're setting the stage for a chemical romance. A little heat, a strong acid acting as a chaperone, and those alcohol and carboxylic acid molecules are ready to react and create a beautiful ester. So what's the outcome of this chemical reaction?
You end up with an ester, and water is released as a byproduct. It's like a chemical equation for a happy relationship.
I love your analogy. So esterification is how we get those amazing smells in fruits and flowers. But are there other applications for this reaction?
Absolutely. Esterification is used in tons of different industries. For example, it's used to produce polyesters, which you find in fabrics, plastics, and films. It's even used to make biodiesel, which is a renewable fuel made from things like vegetable oils or animal fats.
Wow, so esterification is not just about pretty smells, it's also playing a role in creating essential materials and even alternative fuels. Okay, we've covered esterification. Are there any other key organic reactions we should talk about?
Yes. Another important one is saponification. This one's the basis for making soap.
Soap making. Now that sounds interesting. What happens in saponification and how does it lead to soap?
Saponification is essentially the reverse of esterification.
Okay.
Instead of making an ester, you're breaking it apart, and it's this process that's used to make soap.
So it's like a chemical breakup, splitting the ester back into its original alcohol and carboxylic acid. But how does that make soap?
Okay, so in soap making, the esters we're breaking down are called triglycerides.
Triglycerides, those are fats and oils, right?
Exactly. And when these triglycerides react with a strong base, like sodium hydroxide or potassium hydroxide, in the presence of water, they go through something called hydrolysis.
Hydrolysis, that sounds like water's involved somehow.
You got it. Hydrolysis means using water to break down a molecule. So in saponification, water helps break those ester bonds in the triglycerides.
Okay, so we've got triglycerides, strong base, and water. What happens next?
The triglycerides are broken down into glycerol, which is an alcohol, and what we call the sodium or potassium salts of fatty acids. And you know what those salts of fatty acids are? That's soap.
So soap is basically a result of breaking down those triglycerides with a strong base. That's amazing. But how does soap actually work? What makes it good at cleaning things?
Soap molecules have this really unique structure, allowing them to interact with both water and oil. One end of the soap molecule is hydrophilic, which means it loves water.
Right, hydrophilic, water-loving.
But the other end is hydrophobic, meaning it hates water and loves oil instead.
So it's like a double agent. It could be friends with both water and oil. That's so cool.
That's exactly what makes it such a good cleaner. When you mix soap with water, the soap molecules form these tiny clusters called micelles.
Micelles, what are those like?
Well, in a micelle, all the hydrophilic ends of those soap molecules point outward towards the water, and all the hydrophobic ends bunch up together in the middle.
So it's like they form these tiny little bubbles with an oily core and a watery shell.
Exactly. Now, when you put that soap on something dirty, those hydrophobic ends attach to the grease and oil, while the hydrophilic ends stay mixed in with the water. This lets the soap lift the dirt and oil up and away from the surface and into the water, where it can all be rinsed away.
It's like their little cleaning crews, grabbing the dirt and oil and carrying it off.
Haha, that's a great way to picture it. And that's basically how soap works, all thanks to the reaction of saponification.
That's incredible. We've covered so much today, from the basic structures of hydrocarbons to the complexities of functional groups and these amazing organic reactions. I even learned how soap works. I feel like I'm ready to tackle that AP Chem exam. Anything else we should go over before we wrap things up?
Well, just to make sure you're extra prepared, there's one more concept related to ethers that we should touch on. It's the difference between symmetrical and asymmetrical ethers.
Okay, I think you mentioned that earlier. Can you remind me what makes an ether symmetrical or asymmetrical?
Definitely. Remember, it all boils down to those two alkyl or aryl groups that are attached to the oxygen atom in the ether. If those two groups are identical, like two methyl groups or two ethyl groups, then we call that ether symmetrical. Think of it like a perfectly balanced seesaw, same weight on each side.
All right, so symmetrical ethers have matching sidekicks for their oxygen. What about those asymmetrical ethers? What makes them different?
Asymmetrical ethers are the ones where those two groups attached to the oxygen are different. It's like a seesaw with different weights on each side, throwing things off balance. For example, if you have a methyl group on one side and an ethyl group on the other, that's an asymmetrical ether.
I get it. So it's all about comparing those two groups. If they're the same, it's symmetrical different, it's asymmetrical. But does this actually make a difference? Does it change how the ether behaves?
It can. For instance, symmetrical ethers tend to have boiling points that are a bit higher compared to asymmetrical ethers, assuming they have the same number of carbon atoms, of course.
Really? So those symmetrical ethers are a little tougher to boil. Why is that?
Well, it has to do with how those molecules are shaped and how tightly they can pack together. Symmetrical ethers are often a bit more compact and can fit closer together.
Okay.
This leads to stronger attractions between the molecules, and that means a slightly higher boiling point.
So even a small difference in those groups attached to the oxygen can affect the physical properties of the ether. Are there any other times where that symmetrical or asymmetrical difference is important?
You're right on the ball. In some chemical reactions, especially when we're talking about breaking that ether bond, symmetrical ethers might react a bit differently compared to those asymmetrical ones. But for the most part, the main differences you'll see are in those physical properties, like boiling point and sometimes melting point.
Okay, so it's good to be aware of that symmetrical versus asymmetrical thing, especially when I'm comparing different ethers. I feel a lot more confident about ethers now.
Excellent. Remember, organic chemistry is all about those patterns and connections. Once you understand the basic concepts, you can apply that knowledge to all sorts of molecules and reactions.
And that's what the deep dives is all about, helping you see the big picture and how everything fits together.
I couldn't have said it better myself. So as you're getting ready for that big exam, remember to focus on those key organic chemistry concepts, the structure and bonding of those molecules, the different functional groups and their properties, the major types of organic reactions, and don't forget those naming conventions. Practice naming compounds, visualize those reactions, and don't be afraid to draw things out. It can really help solidify your understanding.
That's great advice. And remember, listeners, even if organic chemistry seems a little intimidating at first, it's an incredibly fascinating and rewarding subject. Once you start to understand how these molecules connect to the world around us, it can spark a real passion for science that lasts a lifetime.
I totally agree. Well, on that note, I think we'll wrap up this deep dive into the amazing world of organic chemistry. We hope it's been helpful, and we're wishing you the best of luck on your exam.
Thanks for joining us on the deep dive. We'll get you next time for another exciting journey of discovery.
It really does come down to those groups, on either side of that oxygen, if they're the same, symmetrical, if they're different, asymmetrical.
Right. So like two methyl groups would be symmetrical, but a methyl and an ethyl group would be asymmetrical.
You got it. But does it really matter?
That's a great question. Does being symmetrical or asymmetrical change anything about how the ether behaves?
It actually can, yeah. Symmetrical ethers, they tend to have higher boiling points than asymmetrical ethers if they have the same number of carbons, that is.
Wait, so why would symmetrical ethers boil at higher temperatures?
Think about the shapes of the molecules, symmetrical ethers. They're usually more compact, so they can pack in closer together.
Makes sense.
So you get stronger attractions between the molecules, and that means a slightly higher boiling point.
So a tiny change in those groups can tweak the physical properties of the ether. That's fascinating. Are there any other times where the whole symmetrical versus asymmetrical thing comes into play?
You're really paying attention. Yeah, in some reactions, especially if you're breaking that ether bond, symmetrical ethers might react a little differently. But for the most part, the big difference is in those physical properties. Like we said, boiling point, melting point.
Got it. So it's important to remember symmetrical versus asymmetrical, especially when comparing different ethers. All right, I feel much more confident about ethers now. Thanks for all the explanations.
Of course, happy to help. And remember, it's all about those patterns and connections, and once you've got those basic concepts, you can apply them to so many different things in organic chemistry.
That's what the deep dive is all about, helping you see those connections. Okay, we've covered so much today. Any final words of wisdom for our listener before they head into that exam?
Absolutely. Just remember, organic chemistry, it's all about logic and patterns. Really focus on those fundamental concepts, how organic molecules are structured, how they bond, the different functional groups and their properties, the main types of reactions, and don't forget those naming rules. Practice naming, visualize those reactions, draw things out. It really helps. You've totally got this.
That's great advice. And hey, listeners, even if organic chemistry seems intimidating at first, it's a truly fascinating subject. Once you start to see how all these molecules relate to the world around you, it can really spark a lifelong love of science.
Couldn't agree more. Well, I think that about wraps up our deep dive into the world of organic chemistry. We hope you found it helpful, and we're wishing you the best of luck on your exam.
Thank you for joining us on the deep dive. We'll see you next time for another exciting journey of discovery.